at a, x minus h plus k kind of idea. So we're going to talk about those in two ways. First, what you saw them do to the absolute value function, and then relate that back to the transformations that we were talking about before. So everybody saw different shifting and things happening on their graphs, okay, kind of in groups. So, for example, we saw the parent function, and then we graphed all of these functions. The first group I would concentrate on is looking at like numbers 2 and 3, okay? So what changed in numbers 2 and 3 compared to the parent function? The a value changed, and then what did you say, Megan? And if it went up or down. So what was affecting whether the graph went up or down? A, if it was negative or positive, okay? And do you guys remember from your transformation sheet what multiplying by a negative, what transformation we said that was for a function? It was a reflection, okay? All right, so that's why it was getting flipped instead of upward. The v was all of a sudden going downward. So would you guys say that this reflection was horizontal or vertical? If it was facing up and then now it was facing down, did you flip it vertically or horizontally? Vertically. Okay, so this is a vertical change happening out here. Okay, a vertical reflection. And which axis does that mean it was flipped over? The x-axis or the y-axis? The x-axis. Okay, so just thinking about those different ways that people could phrase it, because all those things kind of mean the same thing, right? What else did the a value do? So if the a was negative, it caused a reflection. What about a 3 versus a 2 versus the parent function that was a 1? How are those numbers affecting your graph? So like, how was number 2 different from number 1? What's that? Was the vertex in a different place? No. Did it still go upward? Yeah. Okay, so there's issues with if it's wider or if it's narrower. So multiplying something on the outside of the function. This 3 is outside of the absolute value, not inside of the absolute value. Okay? Multiplying something outside of the function. What kind of transformation was that? Look at your little blue papers if you have to. So pull them back out. If a value, we're calling it a, multiplies your function, not inside of it, but outside of it, what kind of transformation would we expect? A vertical stretch or compression, okay? And this one happens to actually be a stretch. Your graph is getting a little bit steeper when the a value is 3, okay? All right. So looking at the next group, looking at 4 and 5, what was being adjusted in number 4 and number 5? Which value was changing from the parent function? The k. All right, so these values out here. How was that affecting the graph? Shelby? Good. It moved the graph up or down. Okay, and so it was like a shift, right? And number 4 moved it up 1 space, and number 5 moved it down 4 spaces, just like what you see, right? Like what you see is what you get. +1 goes up 1, -4 goes down 4. So if you look at your transformation sheet, okay, we had 2 types of transformations where we could add or subtract stuff inside the function or add or subtract stuff outside the function. This stuff is being added or subtracted outside the function, like after the absolute value is done, and it moved our graph up or down. Okay, so we have to kind of remember that. Then if we look at the last pair, 6 and 7, what value is changing from the parent function in these graphs? H. Now, what is H in number 6? Good, it's actually -3. Okay. So why that is, remember that the formula said inside the absolute value was x minus the h value. That means whatever h value I pick, I should be able to write x minus that number, and it should look just like my function looks in the equation. What number would you have to plug in right here to make this transform and look like x plus 3? Yeah, if I just put a +3 in here, is that the same as having x plus 3? It says x minus 3 when I put a +3 in here. If I put a -3 in here, is having x minus -3 the same thing as having x plus 3? That's the same, okay? So the h value here is actually negative. why they would make it that confusing, they're not doing it on purpose. When you guys graphed this, what happened to this graph compared to the parent graph? It moved over 3 to the left or to the right? The left. Do you see why they have to make the formula like this so this comes out to be negative 3? That's how we understand it shifted to the left instead of to the right. Okay? So what happens, what's our h value in number 7? Positive 2 or negative 2? Positive 2. Okay, x minus what number is going to make it look like this, and that would be x minus a positive 2. So the h value here is positive 2. And does that make sense with what you saw graphically? Did your graph get shifted 2 to the right? Yeah. Okay, so they didn't put this whole x minus h here to be confusing. They put it there because if they make it x minus h, the number you get for h actually explains which way the graph is going. Okay? So that's stuff inside of the absolute value, a little more confusing than the stuff on the outside, right? Okay? So this is our horizontal shifting that's happening here. So on the back of it, okay, you can determine why they call it a rebound function. But how do you know if it'll open up or down? What determined if the v would go upward or downward? Okay, so if a is greater than 0, it's going to open up. If a is less than 0, it's going to open down. All right, so again, A is positive, upward, A is negative, downward. And then we want to look at the A's, H's, and K's and go back to our transformation sheet to add in all the rest of the information we were missing. So how else did A affect the graph? So we already know it's going to determine if the graph goes up or down. And then we have to determine some other. All right. How else does A affect the graph? We talked about it. We said, yeah, if it's negative or positive, determines up or down. Okay, yeah, so Megan's going like this. It also determines our width or narrow, right? Okay, we saw numbers of 3 and 2, and that made our graph more narrow. So whether A was negative or positive, if its value was bigger than 1, okay, it was making our graph more narrow. Now, instead of saying more narrow, I want us to talk about, is that a vertical stretch or a vertical compression? It's vertical because the A was outside. So if I'm making the graph more narrow, the V is getting, am I stretching it or am I compressing it? Stretching it, right? Think about grabbing that paper top and bottom. So this is going to be a vertical stretch. Whereas if it was less than 1, then what would happen is we would have the vertical compression. Okay, so then we looked at H. Remember that H was the value happening inside of the absolute value. So when we add or subtract something inside of the absolute value, what did it do to our graph? What's that? Okay, so it shifted our graph left and right. The transformation, we called that was a translation when things were being shifted. Okay? So when H was bigger than 0, but remember it's a little tricky to figure out if H is bigger than 0 or not because of the minus sign right there. But when H was bigger than 0, we were translated to the right, like a positive number would go to the right. And when H was less than 0, so if it was a negative value, we were translated to the left. Then remember, K was what was added on after the absolute value. So the absolute value part's all done, and then we're looking at what ends up over here after the function. So when it's added on at the end, when the function is complete, that was shifting us up and down. So again, if K was bigger than 0, still a shifting, so it's still a translation. So it's being translated up. And if K is less than 0, then we are translated down. Okay. Yes, sure.
You said the absolute value of A, but how could the absolute value of A be less than
Like 1/2 or 1/3 or something. Something between 0 and 1. Yeah. Okay. That's okay. It's good that you asked. So do we understand how these changes work? So this is kind of a better perspective. We talked yesterday a lot of it with like weird notation, and now you've kind of seen the notation in effect. So two things that we should be able to do with this. We should be able to go back and understand all the transformations we talked about yesterday, and we should be able to graph absolute value functions by hand. Okay? So we're going to graph an absolute value function by hand. So if you look at the bottom of your page, we're going to pick one of those to graph by hand. I'm actually going to choose this one. All right. So the purpose of us using the calculator was to find all these patterns to make it quick for us to do this on our own. Okay? So first of all, notice that this isn't the best example because the 2 is stuck inside the absolute value, and that's not how we looked at any of them. But absolute value has a special property that taking the absolute value of 3 times 2 after the multiplication is done is no different than taking the absolute value of each one and then multiplying them. Because what does absolute value do? What does it affect in your answer? Does it affect the number part of your answer? Just the signed part of it, right? So would it matter if you turned it positive at the very end of the multiplication problem, or if you turned everything positive before you multiplied them together? No. Okay? So how that's going to help us, and the reason I'm showing you this is in case you have one like this on your homework. So how this is going to help us is we have our 2x minus 4 inside the absolute value bars, and what we want to do is we basically want to factor out this coefficient so we can get that a, h, and k value just like we did on the problems you were just doing. Okay? So we're going to factor out a 2. No choice. I need this coefficient gone. I just want x plus something or x minus something by itself without a coefficient. So it doesn't matter if 2 nicely goes into this other number or not. The 2 needs to be what I factor out. Okay. Lucky for us, 2 actually goes into 4 very nicely. What would it leave us with as the second term here? So it's minus 4. We're factoring out a 2. We're going to be left with minus 2. So you might think, well, that didn't help us. The 2 is still in the absolute value. But now what we have in the absolute value is a little multiplication problem. 2 is one of the factors, and x minus 2 is the other factor. And we said over here, if you have a multiplication problem, it doesn't matter whether you take the absolute value after you multiply or whether you separate them out. So I can separate the 2 as its own absolute value and the x minus 2 as its own absolute value, still multiplying each other. And so the reason that that's helpful is because the one that's just a number, I can find the absolute value of it because I know how to do absolute value. So the absolute value of positive 2 is still positive 2. Okay? So this is just something that you can use to help you transform any absolute value function into this a, h, k form. All right? Then once you look at it, you should be able to pick out the a, the h, and the k values. All right? So what is the a value in this equation? 2. What is the h value? Positive 2 or negative 2? Positive 2 because it already accounts for a minus sign in the formula. And what is the k value? 3. So the parent function would start at 0, 0, but our function's not going to start at 0, 0 as the vertex. Why not? Why is our function not going to start at 0, 0? Okay, so the h is 2, which is going to shift us where? This one doesn't shift us up. This one shifts us the right. Okay, so we're getting shifted to the right 2. This one is going to shift us up 3. So instead of our vertex being at 0, 0, we're going to move from there 2 to the right and up 3, and that's where our vertex is going to be. So notice our vertex is going to be at 2, 3, which is our h and our k values. Serena? Yeah, well, at this time it just happens to work out that way. But if this was a negative 2, it wouldn't be the same. So it's important that we factor it all the way out. All right, so our vertex is at 2, 3. Is this absolute value function going to open up or down? Up. Do you expect it to be the same width as our parent function, or do you expect it to be vertically stretched or vertically compressed? Vertically stretched by a factor of 2. Now, since this is absolute value and the sides are lines, they normally have a consistent slope. And in the parent function, the slope is every time you go up 1, you go over 1, right? And you just keep using that slope to get the whole line. In this case, we're doubling it vertically. So what we're going to do is we're going to go up 2 instead of 1, but still just over 1. So I can almost use that 2 like a slope, okay? Except for that once I do this line, remember it's a V. Don't continue the line down on the other side. You should have the other side of the V symmetrical to this. So just plot a point that would be the mirror image of the other, and then graph that. So you can use the H and the K, should give you your starting point, your vertex. If the A is negative, you know that the V should go downward. If it's positive, you know it should go upward. And you can use this A value here, because the sides are lines, you can use this as the slope. Now, when we get into things that are curved on the sides, we can't just keep using that A value as slope. But we can here, and it gives us a really quick graph of absolute value. Like, I can do this as fast as it would take me to type it into the calculator and get that absolute value function, because I can pick out those numbers just as quickly. Okay? Does that make sense about how the absolute value would work? Yes? All right, then I want you guys to graph one more. I want to go back to the one where the number is already factored out of the absolute value, which is this one. All right, so try to get this one on your paper. Again, you want to identify A, H, and K, and then you want those tools to help you get the graph quickly on the paper. All right, so the important things that you should pick out, the A, the H, and the K value. Notice that the H value is -3. The H and K value give me the X and Y coordinate of my vertex, so I plotted it at -3, -1. I knew my V should go downward because the negative part of the A means a vertical reflection, so from upward to downward for the parent. What is the value of 1/2 tell me is happening to my graph as far as transformations go? So it's out in front, so it's vertical. Is it a stretch or compression if it's 1/2? Compression in this case. That's why you see this get a little wider than the parent function. To get exactly where it is from your vertex, you can use it like a slope, down 1 over 2. Make sure you have a mirror image and you create that V. Sorry.